All right, let's go ahead and talk through some of the information necessary to complete a selection of potential test questions for test 1 for the lab. Okay, so for this first question, we have a student who's making a measurement on a pencil, estimated somewhere around 18 centimeters, and the ruler has a certain way that it can measure. So we're going to talk about the difference between accuracy and precision a little bit later. We just want to understand that anything that we measure in a lab is going to be an approximate value. There's going to be some kind of guess involved, and you can never measure something exactly perfectly. Now, there are some things called exact values, and these are things basically that are given to us or things that can't possibly be wrong. So something that's part of a definition or a conversion, so something like saying that there's 12 inches in a foot is exactly true and something that we completely trust. And then another example of an exact value is something that has been counted. So you can't have, say, 13 and a half people in a room. It doesn't make sense. You have either 13 or 14 or 15 or so on. Okay, so this approximate measurement, again, somebody's using a ruler to measure a pencil. We have 0.01 centimeters listed as the way that we can measure. And we want to keep in mind that this is two important pieces of information. First, that our measurement needs to have 2 decimal places. So from that, we can eliminate a couple of choices. This one only has 1 decimal place. This one has 3. So only 2 choices remain that have the appropriate number of decimal places. Then the second important piece of information is what units, if any, we want. So sometimes we actually don't want any, and in this case we do. So this measurement is not going to be correct. Potentially a trap there because it says around 18 centimeters, and that's obviously the closest to 18 as a number, but it doesn't have exactly the right format. Okay, then we need to understand a couple of things that we can build up to finding percent error or percent difference. So first, before we can do that, we need to know how much difference there is between a measurement and an accepted value, and then eventually we'll find percents based off of that. So here, absolute value means we don't care about it being too big or too small, or positive or negative. We just want to record the difference. That also technically means that in your subtraction, the order doesn't matter, because if you did subtract the wrong way and you got the wrong side, this absolute value part would basically cancel that anyway. Okay, now a couple of things to pay attention to. If we are subtracting different things, we need to have matching units, and we need to keep those units. So the only thing I can subtract away from centimeters is a different number of centimeters. I need to understand that's going to give me an answer of centimeters. So from that, we can technically eliminate 2 of these choices. Then we need to be careful because we need to pay attention to the placement of the decimals that we have in these numbers. So like I said, we're going to give a better definition to this later. But if we're taking a measurement out to here, then any difference we have needs to also look the same way. So keep in mind, like the previous question, we talked about the 0.01 centimeter precision. Again, we're going to define that better a little bit later on. Basically, we want our answer to also look like that. So if you subtract these in the calculator, it's going to tell you just 0.3. But we need to keep in mind that our answer needs to look like the things that went into it. And so we do specifically need to have the 0 on the end, which makes this one wrong and this one correct. Okay, and then finally, to find the actual percent error or percent difference, technically, there's some variation on how this formula can look. Again, the fact that we use absolute value in our formula means that the order of the subtraction is not super important. What you want to remember from this is that we're looking for an absolute difference first, right? So we want to find the difference by subtracting. Absolute value means always positive, which fixes it if you accidentally subtract the wrong direction. Okay, then technically we get a difference which we want to turn into a decimal. So we're going to divide by something, and then finally to get percent, we're going to multiply by 100% at the end, which basically means multiplying by 100 and slapping a percent sign on it. Okay, now let's look at these values. The one that we trust to be correct is the one that we use more often. So that's actually going to show up twice in our work. We use it to find our difference, and then we divide by it to find a decimal, which is on the way to finding that percent. So the thing that's supposed to be correct, the thing we trust more, is the thing that we use more. And then the thing that we're checking only gets used once. Okay, so remember, we've already technically done the first step of this because these numbers are connected to each other in this particular question. But finding that difference, we'd have 0.30 centimeters. Then we would divide by 17.94 centimeters, and then we'd multiply by 100 and slap a percent sign on it. So I want you to see from here that we're dividing centimeters and centimeters. That means that the units from here go away. The only thing we have left really to call units are, just really just a percent sign. Okay, and then now dividing these two is going to get you a number that's 0.01, something very small. Don't forget to either bump the decimal 2 times or multiply by 100. So a lot of times students will make a mistake here. They learned, way back when in school to bump the decimal 2 times over. You don't want to do that and multiply by 100, or else you get like 100 and something percent here. So do one or the other, and then your correct answer for this one should be 1.67%. Okay, then let's talk a little bit about how measurements are taken. So the rulers that we have in the lab, again, going back to earlier information, you have 0.01 centimeter precision. So that means that any measurement you ever take with any of these rulers in the lab should always have 2 decimal places and a cm for centimeters. So technically, we can eliminate those two. It is a very common bad habit that is wrong that students will just click the latch on to the closest line and decide that that one's the measurement. It's not. It's almost never going to end in a 0. Typically, there are random sorts of numbers on the end. Now, it's always a little bit of a guess what the measurement is because it's hard to see between the lines, but it is something that you can definitely do. Okay, so let's think about this right quick. If I have some measurement that is somewhere after the 18 centimeter mark, then you want to think about the centimeters almost like being like dollars. Think about money. So if it were perfectly on the centimeter mark, 18 centimeter mark, it would be 18.00 centimeters. That is almost never going to happen. But that's what the measurement would be if it did. All right, so that's just sort of the base of our measurement. Notice it doesn't really match anything. So we want to read some more information and see what else is going on. If it's talking about here, the 8th line after that, there are marks between the centimeter marks. If you're thinking about money, then it's kind of like dimes, right? 10 cents, 20 cents, 30 cents, so on. Technically, they are portions of centimeters. Millimeters, depending on how you write out the answer, but we're going to rate them as portions of centimeters. So each line is like 0.10 centimeters, 0.20 centimeters, 0.30 centimeters, and so on. So I hope it makes sense that if we're talking about the 8th line, that would be 18.80 centimeters. Okay, and then read the question a little bit further. One little tiny piece of information remains. It is barely after this mark. And so that means that it's not exactly on the line, it's a tiny bit after, which is what's going to happen in most of the measurements that we're somewhere between these values. Then we're going to see 18.81 centimeters. Okay, let's try another example. So we have a few of these that we want to look at for different ways the lines can sit for what we're measuring. So this one mentions the 16 centimeter mark. Okay, so if we get started with that 16 centimeters, if it were a perfect measurement, and again, they almost never are, then that would be 16.00 centimeters. Okay, then we start reading a little bit more. It's talking about between the 7th and 8th lines. So that means it's somewhere after the 7th line, somewhere before the 8th line. 7th line would be 0.70, 8th line would be 0.80, and it's somewhere between that. So again, we want to keep track of this. We'll bring this information down. So far, we know it's 16.70 something. We want to read the rest of the information to see what that final decimal point is going to be. So it says just before halfway between the marks. So think about this, right? If the first mark would be 0.70 and the second mark would be 0.80, then the middle of that would be 0.75. Now be very careful here because it is an answer choice, but it says just before there. So just before 0.75. Think about money. What would be just a little bit less than 75 cents? Well, that of course would be 74 cents. And there we go. So be careful. Some of these answer choices are potentially traps. Normally you can eliminate 2 right off the bat. You keep talking about how the rulers have 0.01 centimeter precision. So those can't be it, but we have to be careful to read to see which one we really do want. All right, so now last little one in the group before we look at something slightly different. We have, okay, here talking about the 14 centimeter mark. So again, if it were perfect measurement, which it probably won't be, that would be 14.00. Think about money. Exact $14 would be $14.00. Then it mentions the 6th line. Remember, each line between the marks is like a dime. So 6 dimes would be like 60 cents. We're going to put this together and see what we've got so far. So our measurement is somewhere around 14.60. Then here, last little bit we need to hone in on the information. It is just before that mark. So think about it. What would be a tiny bit less than 60? Well, that would be 59. So 14.59 centimeters. Okay, so this question is just a quick review on the way that you should find error, or percent difference, different names for basically the same idea. You want to remember the way that we set these up. A couple of the clues. The thing that's supposed to be the answer needs to be used twice. So we can eliminate this first answer choice because that's not what's divided on the bottom. And looks like also this one. Okay, so we've got it narrowed down to 2 choices. If you're finding percent error, then another really big clue is there should actually be a percent in it somewhere. So this one is missing the multiply by 100%. Okay, so technically that gives us an answer, but I want to talk about the final thing that is incorrect. So the way that we set these up and the way our formula reads on the formula sheet, we specifically need to have absolute value. So we don't care if something's too big or too small. We want to know just how much is it off. So these were supposed to be absolute value bars, these vertical lines instead of parentheses, which technically just further confirms that that's the one we were looking for. Okay, so now a handful of questions that are of a completely different sort. So we're dealing with a little bit of trigonometry in this first group of information, and sometimes that's a little bit difficult to deal with, but it's something that I think we can handle. So if you don't have a shape in front of you, there's no worksheet, there's no picture, there's nothing else for you to specifically use, then what I always do is I draw just a generic triangle. I don't care if it's to scale. The thing I need to know is the orientation and how the different pieces relate to each other. Okay, so there's just a basic triangle. It is a right triangle because we don't have the tools necessary to deal with any triangle that's not with a 90-degree angle. Then just to have a place to put it, we'll say that the reference angle or important angle is here. And then the Greek letter theta, it's kind of like a circle with a line through it, is typically used to represent angles. Okay, one of the good things about drawing your triangle like this and always using the same orientation is that when you look at this triangle, then you know that adjacent, opposite, and hypotenuse are always in the same orientation. Adjacent means next to or touching the angle, and the way that we draw these pictures, that's always going to be between the mark for the special angle and the mark for the right angle. Then the hypotenuse is always the longest side, and it always happens to be out from the right angle, or in this orientation is the side that looks slanted. Then the leftover side is the opposite one. There's also a trick you can use where you run around and you say AO. So AOH is a way to label these triangles. Well, like I said, if you always draw them this way, you can always make their orientation like this, and that's helpful so that we can pick trig functions and we can do some work. Okay, then let's read through this a little bit and see what's important here. So find the hypotenuse, all right? That means that I'm interested in this side. In a triangle that has an 8-meter side across from the angle, okay? So across means out here. Be careful, it's not A for across, it's A for adjacent, which would mean touching or next to. And this is 8 meters. Then it does go ahead and mention 67 degrees. I didn't really leave a lot of space to rate that, so I'll squeeze it over here. That's 67 degrees. Okay, then the next thing we need to do is pick a trig function. So there are a lot of different tricks for this. Sometimes people make funny words out of them, so, ka, toa. The biggest thing that we want to do, though, is we want to see which sides are important for us, right? So we're not looking at the adjacent side. That's a clue that these two probably aren't going to work. But just to confirm, we have the opposite side that has a number, and the hypotenuse has a question mark. Now, you have to be careful. Don't avoid the hypotenuse. You need to use the hypotenuse because that's what we're looking for. If our variable that we're trying to solve for is not somewhere in our work, then it's impossible to find. So it's very important to make sure you don't skip the thing that we're looking for. Okay, then what this function means, the SOH, this abbreviation is sort of a verbal shorthand. The S is for the sine function, which is typically abbreviated SIN. And it can't be sine function on its own, it always has to be sine of something. So typically sine of theta is equal to, then the O and the H means the opposite side length over the hypotenuse. So that's our function that relates to this funny word right here. And then when we start to plug into it, we're going to commit to the sine function. We're going to keep using sine for the rest of this question. We don't mix and match with these. Then theta is the angle. We are told that this one is 67 degrees. Then the opposite side length was 8 meters. And then the hypotenuse is just h. That's what we're looking for. If you want to, you can put, x or something as a, excuse me, as a variable to look for. Okay. Then what we have is a super duper, excuse me, ugly looking fraction. I know it seems like a bad idea, but if we turn everything into fractions, then we can make this look like a proportion and we have a method for solving. So nice thing is proportions are a little bit funny. Anything that's diagonal can be traded, right? So I can swap these in their positions. And I can make this, instead of sine of 67 here, I can put that in the bottom of this fraction. And the h will move up there and take its place. So that will tell me that hypotenuse is equal to 8 meters divided by sine of 67. Now, I have no idea what sine of 67 is. That's not something that I have the ability to find, and I assume you don't either. So we will use a calculator. Okay, so we're going to leave the 8 meters alone because we understand what that part is for now. It's the sine of 67 that we're not sure about. So if we take sine of 67, on some calculators you can type that in order. On other calculators, sometimes you have to do the 67 first and then hit the sine button. If you get a negative answer or something strange, you need to make sure you're in degrees mode. But this is something you're going to need to figure out how to do because we're going to have trig a little bit in almost every module. So sine of 67, just that part, is 0.9205. Then finally we can get an answer. If we take 8 divided by this number, then we get 8.69 meters, plus or minus a tiny bit depending on decimal places. So a couple things to watch out for. You want to make sure that you write down at least 4 decimal places on this. This is going to fill up your calculator screen and go on forever. If you're comfortable with your calculator, there's a little bit of a trick you can often use to not have to type this number back in. You can either store it or flip it or rearrange your functions slightly. If that doesn't make any sense to you, then that's fine. Just write down a bunch of decimal places in Scratchwork and then divide manually. Then we also know that there was no way that either of these were ever going to be answers. The hypotenuse is always the biggest side, so it could only ever have been bigger than 8. All right, and then this one ended up being the one we were looking for. Okay, then, like I said, we do have a couple of these to look at. So we've got another one that hopefully is using a different function. So let's see if we can get some practice with each of them. This one, I'm going to draw out my generic triangle shape first. I don't care if it's to scale. I don't care if the sides are the right length and proportion against each other. Does not at all matter to me. So I just basically need a place to write stuff in. Then remember, with this orientation and the way that we draw this out, that these are adjacent, opposite, and hypotenuse as our sides. Okay, so now find the side touching the 54-degree angle. Okay, that gives us two things. First, we know that's 54 degrees, and we want the side that's touching it. So we're going to go here. And you might ask, well, okay, well, what about that other side that's touching it? But that side has a fancy name. That's the hypotenuse. It's out from the right angle. It's the biggest side. It's the one that kind of looks crooked with this orientation, but that's special on its own. Okay, so we're looking at this adjacent side, the one that's next to or touching the angle. It says find it, so we don't know what this is. For algebra, which is what this is eventually going to boil down to, there needs to be something missing or you're going to get stuck. Then it says that there's a hypotenuse of 25 kilometers. So the hypotenuse is the longest side, and we have a value for this one, so equals 25 kilometers. Okay, then it potentially helps to look at your funny words again. So TOA for our trigonometric functions. If you look, we can eliminate the opposite side. There's nothing here. There's nothing to solve for. There's nothing to get. There's just nothing to do here. So we don't want either of these is how it seems. If we go back and double check this one with the C in it, we're looking for A. So remember, in algebra that's good, we need to have a goal or something to solve for. So don't discount this one. Don't get rid of it because we don't know A. A is a variable and plugs in just like numbers when you're dealing with algebra. Then H is 25 kilometers. That's a number you can drive, or if you're adventurous, run 25 kilometers. I mean, I don't want to, but somebody could. And so that's a number that we can measure out or see. All right, so that looks like our function then. The full version of this, cosine, is abbreviated typically COS, cosine of theta. So it has to be cosine of something, and theta is typically what we use to reserve angles. Then the A and the H means that this is the adjacent side length over the hypotenuse. Okay, so if we fill this in a little bit at a time, cosine of theta, so that's our angle, in this case that's 54 degrees, cosine 54 degrees. I'm going to fix my handwriting there though. So 54 degrees is equal to the adjacent side length. So that's A. We didn't get a number for this one, so we can't do any better than that. And then divided by the hypotenuse, which is 25 kilometers. Then again, we can't really do anything with A divided by 25. So if we can't get rid of that fraction, we're going to go all in and make everything a fraction. And proportions have this weird rule. We can swap these diagonal terms. Okay, that works because even if you were to go back and, oh, no, sorry. Look, we don't want to do that this time. The A is on the top. So we want to solve for this thing, then actually normal proportion rules cross multiply. That's going to be great here. So if we cross multiply, A times 1 is just A. And then in the other direction, we're going to have 25 kilometers multiplied by cosine of 54. Okay, now I know what 25 is, but I have no idea what cosine of 54 is, so that's something we will need to use a calculator to find out. So we'll have 25, then cosine of 54. Again, hopefully you figured out this process in the last question, but you'll either type in cosine 54 and hit equals, or you might have to type in the 54 first, hit the cosine button to make something happen. But if you can make that work, this should be something like 0.5878 with some slight rounding. So again, this probably fills up your whole calculator screen. If we round to that spot though, and multiply these together, we get 14.70 kilometers. Okay, well, because we rounded that a little bit short, depending on how you type this in a calculator, your answer may be a tiny bit off, but I think it's obvious then which one is the closest. Okay, then let's see what this one's doing. So generic triangle. Theta to mark our angle, and we want to see where our right angle is. And then because of the way we drew the picture and set the angles, adjacent, opposite, and hypotenuse will be these. Okay, then let's see what we've got. So the side across from, all right, that's out here. So we're looking for our opposite this time. The angle is said to be 66 degrees, so let's squeeze that in. And then the angle touches, so adjacent means next to or touching. This is 5 centimeters. Now, we just drew this triangle randomly. We don't right offhand know if the answer is bigger or smaller than 5. Looks a lot bigger with the way the picture is drawn, but we want to look at our trig functions and find out without having to guess. So, ka, toa. Excuse me. All right, so ka, toa, look, we can't use the hypotenuse here. You might think we can't use O, but you have to remember trying to solve for something. So O is actually the most important letter here. We need to find that thing. So if we can't use the hypotenuse because we don't know what to plug in, then that's not going to work, and that's not going to work. So I really hope that our last option does. So if we look, O is what we were trying to find, which means we definitely need that. That's important. And then A is 5, which you can hold up, 5 fingers or 5 centimeters, about half the width of your hand. We can count that. We can measure that. That's definitely important information. Okay, then what that tells us is that the tangent function, tan is usually the abbreviation there, of theta, so that's the t part, is equal to the opposite side length, that's the O, over the adjacent side length, which is the A. Okay, then we want to see what we can plug into this to see how we can solve. So tangent of our angle, which is set here to be 66 degrees, so tangent of 66 degrees, is equal to the opposite, just O, because we don't know what that is, over the adjacent side, which is 5 centimeters. Okay, so we want to make sure we pay careful attention here. We've got an ugly fraction. We can't do O divided by 5. So if we stick this over 1, we make it look like a proportion. We can use proportion rules to help us. Nice thing about the placement of the variable this time, it's on top. So if we were to cross multiply, 1 times O is just O. And in the other direction, 5 centimeters times tangent of 66. Okay, well, I have no idea what tangent of 66 is. So that's something we'll have to get from a calculator. So far, we know that 5 centimeters is here. Then tangent of 66, again, you'll have to get from a calculator. That's going to come out to be something like 2.246. And then multiplying these together, oops, that's not theta, that's just O, but multiplying these together gives us 11.23 centimeters, which is an answer choice. So there's some practice with each different function. You have to be very careful with the placement of the variables. Make sure you can label these sides. That's why it helps to draw sort of a generic triangle the same way as often as you can. Then pay careful attention in the steps to solve. So if you're looking for the variable on top, like we had on this one and the one before, then typically you're multiplying to get an answer. So like this one and this one we were solving for A was also on top of that fraction. We just multiplied. The original one, the very first one we did, we were solving for the variable that was on the bottom of the fraction. So notice if we were to try to cross multiply from here, we'd have h times sine of 67. And then that thing would be in the way, we'd end up having to divide by it to move it. So because of the weird way that proportions work, it's exactly equivalent to just swap these places. A nice thing about that is if you swap those, then you get down to something you can fix. It's ugly, but that's what calculators are for. Now, the one thing we didn't talk about, we've used 3 different functions now to find different sides, but what happens if you don't know the angle? Well, I'm glad you asked. So let's take a look at this one. So to start off with, nothing's really different. We're dealing with a triangle, trying to find some missing stuff. So let's sort of ghost in a generic right triangle. Okay, and then with this orientation, we've got adjacent, opposite, and hypotenuse. And let's see if we can fill in some information. So find the angle means that we don't know theta this time. All right, so I'm just going to throw a question mark down. So question mark is equal to theta. It's the angle across from the side. Okay, so across from this O is going to be 19 centimeters. Okay, so this is important. And hypotenuse is 20 centimeters. Once more, think through your trig functions. So, ka, toa. All right, and it looks like the side that we're ignoring, the one we're not using at all, is the adjacent side. So if we look, all right, that's not going to work, that's going to work, not going to work. Just to double check, the opposite side is a number, hypotenuse is a number, and that's good. So writing out this function, sine of theta is equal to opposite over hypotenuse. That's just taking those pieces, basically expanding them back out. What's a little bit weird about this one is that sine of theta, there's no number this time. We're just stuck with that. We're going to end up trying to solve for this thing. As it turns out, it's not hard to do. We just sort of fill in, get started the same way, opposite over hypotenuse. Technically, we've got 19 centimeters over 20 centimeters, but notice that centimeters would cancel, and that's not going to be super important here. So what's going to happen then is that if we're looking for the angle, like this, solve down this side as much as you can. So 19 divided by 20, we can actually finish that this time at 0.95. Now, it doesn't mean that we have like a 1-degree angle, because that would be tiny. What's going to happen here is we need to get rid of the sine function to find theta. So the opposite of a sine function is something called a sine inverse. So typically it's the same button on your calculator, but it's got a little -1 sign that kind of looks like an exponent. And that's just some horrible, nasty, ugly function that your calculator knows how to do. Thankfully, we don't need to know anything about that specific process. We just know that sine inverse happens to this thing, and it works backwards to give us what the angle must have been in the first place. So plus or minus a tiny bit of rounding, depending on what the numbers are and what you wrote down. This is going to give us 71.81 degrees. So it's a little bit weird to look at, but technically it's usually a little bit shorter in the setup whenever you're looking for an angle. You end up always using an inverse function. So let's say that we'd had different information and we started with cosine, then we would use a cosine inverse to finish. Or if we had another one where we had a tangent function, then a tangent inverse is going to clear that up and give us an answer. You don't at all want to mix and match with these. Okay, then let's move away from that for a little bit. This is a question about vectors, and the number is randomized. It's not super important, 3, 4, 5, 6, 7, whatever. The big thing that we want to take from this is that it's most important where vector points. Whether it's above or below the axis, or to the left or to the right of the axis, doesn't matter. It's where it points. So if we think about just a normal coordinate graph, right, then you probably know the x-axis is the one that's laying down. What might be new here, which you might not have had to pay attention to before, is that we can split this in half. So the right half of this is the positive x-axis, and the left half is the negative x-axis. Then similarly, you might have known that the y-axis was the one that goes up and down, but we can split it to be positive y and negative y. So keep in mind that your positive, that's what this says, positive is going to come from either positive y or positive x. So that's either going to be up or to the right for where it points. Again, that's the really important thing here. Then if we're looking for negative vectors, then that's going to be to the left, or that's going to be down, again, for the direction that these point. So the vector points down or points left to make a negative value. Well, the only one of these that even really mentions where these point is here, and we wanted a positive answer. So yeah, that makes sense. Pointing to the right would give a positive x value and give a positive sum. Keep in mind how this can change. It can ask for negative. It could be in orientation vertically or horizontally. So just use your judgment to see what you need. Okay, then simple question here. Net force. There's not a lot going on here because it just says that this box or crate or whatever this thing is resting. So it's just sitting there, right? So if I have some surface, and let's say that this is my box or my crate, if it's not doing anything else, if it's just resting here, that means that the weight from the box is trying to come down. So weight is equal to mass times gravity. If that was the only force, then it would break through the ground or break through the surface and it would, destroy things, fall down. If it's resting, though, that means that there has some force going up against it. So the force of the surface not breaking technically is normal force. So also has N, but it's different. It's normal force. And in this case, if there's only one force up and one force down, then this thing has to be equal to the weight, which remember was equal to mass times gravity. Now we have to be careful here, is that there are forces acting on this. There's a certain force up, there's a certain force down. But if this thing is resting there, those have to cancel each other out. So there's actually zero net force because the force that's up and the force that are down, they're equal and opposite. They cancel each other. This thing is just sitting there. Net force you can also think of as being like leftover, and there's nothing left over. We've got approximately 500 going up, approximately 500 going down. They cancel each other out. Okay, now net force is really important because it can help us make predictions about how something will move. So net force is also typically set up as part of Newton's second law. So sometimes you'll see this as just F equals mass times acceleration, F equals ma. I've left a little bit of space here because you have multiple forces interacting, then it gets immediately upgraded to net force, again, which can be whatever leftover force there is. Typically there's something trying to help, typically there's friction working against, which partially gets rid of that, but whatever. Okay, then we want to read the question carefully to see what kind of answer we expect for net force here. Mass can't be negative or zero for a real object. It's always going to be some positive answer. And so really it's the acceleration that's going to tell us what happened in here. So because acceleration is change in velocity over change in time, then it's the change in velocity that's really going to dictate the sign on all of this. With an increasing velocity, then that means that the velocity is going up. So that means that my change in velocity is positive, which in turn means that my acceleration is positive, and that's going to mean that my net force is positive. So greater than zero must be positive. That's going to be this one. Okay, then just to really drive in that point, we have this next question, which is similar. We don't have any real numbers for this. Nothing is given for us, but we can use these concepts and we can figure it out again. So net force from this version of Newton's second law is equal to mass times acceleration. Let's think about what this means. Decreasing velocity, so that's going to mean that our change in velocity is less than zero, which is then going to mean that our acceleration is less than zero, which is then going to mean that our net force is less than zero. So what numbers are less than zero? Negative. Okay, then finally, we're going to define some of these things that we talked about earlier. So accuracy and precision, basically ways of seeing how good a measurement is, but looking at it from slightly different sides. So the way that we're going to define accuracy of our measurement is specifically the total number of significant digits it has. This is going to change for different objects. So if you're measuring, say, a feather compared to a boulder, you're going to have different numbers for different objects. So changes for different objects. Okay, so if we have some measurement that's between 60 and 80 grams, but it has a precision of 0.01 grams. So remember, precision basically is telling you how many decimal places you want. So let's make up a number as an example. Let's say that we have 61.23, because why not? Then our number of significant digits is going to be how many different important pieces of information do we have here? So 1, 2, 3, 4. If I had something really heavy, then it would have had more numbers in front, and that would have made the accuracy technically go up from this. We would have more significant digits overall. So for accuracy, technically the units don't matter, but we just needed that to talk about what kind of measurement this might have been. So accuracy, total number of significant digits, 1, 2, 3, 4. For the same measurement, if we're checking precision, then precision basically means like your final decimal place, and then is dependent on units. So we've talked about that without a great definition. It just keeps saying 0.01 grams or 0.01 centimeters for precision. So again, let's make up another number. Let's use the same one as before. Let's say we've got 61.23 grams is our measurement we're talking about here. Then the placement of the last significant digit and the units are going to be the same for anything measured on whatever this device is. So same for all objects. Because even if I had something really heavy and it had more places in front, the measurement would still end in the same decimal place and still have the same units. So look, there's 2 decimal places and a G for grams. Technically, if you're paying attention, this should be a free question. Find the precision, blah, 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 precision. Technically, this answer was given to you. It's based off of the measuring device and not the object itself. So again, another thing that's important to remember from this question. Okay, so now we want to look at a couple of conversions and a couple of questions that we can work out that are eventually going to be dealing with friction. Okay, so we've got an object which is 567.89 grams. So, okay, I didn't work very hard to come up with this random number. But we want to take this thing and we want to convert it into weight. Now, this is an important definition. If we're talking about weight, technically that means we need to either use pounds or newtons. The textbook that goes along with this information pretty much pretends that the customary system doesn't exist. So it means we're looking for newtons. Technically speaking, this conversion only works when we are on Earth, but that is in fact where we spend most of our time. So grams takes 1,000 grams to make a kilogram. Well, because of gravity, 1 kilogram just happens to turn into 9.8 newtons. So this happens because 1 kilogram times 9.8 meters per second squared makes 9.8 newtons. And so it's a little bit of a weird conversion to see here. We don't normally see a conversion where neither of the numbers is 1. So technically this is combining the grams to kilograms and kilograms to newtons conversion, but it does still work. When we do this, the grams are going to cancel each other. Newtons are going to be left over. And what we want to do is we want to multiply each of the things together from the top, and then we divide by each of the things that were on the bottom. So we're going to take 567.89 times 9.8, then divide by 1,000, and technically also divide by 1. If we do that, we get 5.565322 newtons. But because this was something that was presumably measured in a lab, then we need to follow significant digits and rounding. So we have 1, 2, 3, for 5 significant digits in this thing. These don't matter because they're parts of definitions or conversions. So we trust that they are fully correct. So we're not going to use them to limit our rounding. That means that our answer needs to have 5 significant digits. So 1, 2, 3, 4, 5. Notice that we have extra places. So normally you'd want to use, traditional rounding rules. Good news is that the 2's on the end aren't going to contribute. We basically just get to cut the number short. On this one, should not have been too big of a deal because the answer choices are all mixed around from doing the wrong thing with 1,000 or 9.8. So only one of the actual choices was really anywhere close to what we were looking for. This one's, off by a factor of roughly 10. This one's off by like 1,000, 10,000, 100,000. Out of they're really far off. So the only one that really even made sense was this one anyway. Okay, then getting into some of our weird rounding rules for doing different types of steps of arithmetic. If we add things, we follow a certain set of rules, and if we multiply things, we follow a different set of rules. So say I have a wooden pallet with 14.6 kilograms, and I load a whole bunch of stuff on top of it. Then the total mass there is going to go up considerably. We have to be careful because this is asking for weight. So that means we are going to have to go from kilograms to newtons eventually. Okay, but first step, we want to find the total mass. So total mass is going to come from taking the 511 kilograms. I'll leave a little space though so I can line these up better. And then adding the 14.6 on which it sits. Now, adding these the way that they are, you get 525.6, which coincidentally is an answer choice, but be careful. This is total mass. It's not rounded yet, and it hasn't been converted yet. So this is wrong. Now, we want to remember that this is kilograms. So if you had written these units down, again, you would notice that can't possibly be the answer. Okay, so then now, rounding rules with addition use the least precise. So look, this decimal place ends further to the left than the other one, and that means that I want my answer to round here. So that's going to round to 526 kilograms. Okay, then I still need to get to weight. So I need to convert this into newtons. We don't have to go from grams to newtons this time, just kilograms. So we can use gravity as if it's a conversion. We can say on Earth, 1 kilogram turns into 9.8 newtons. This is going to cancel out the kilograms. It's going to give newtons as an answer. Multiplying this is going to give 5,154.8. And then we want to use our rounding rules. So you'll notice at first glance that this looks like it's a little bit off. Well, it's not going to be when we finish up. This has 1, 2, 3 significant digits. I immediately wrote the wrong number. 3 significant digits. So when we multiply, we want to know based off of significant digits, not the placement of decimals, but just how many total numbers there were. 9.8 and this is part of a conversion, so they're not going to limit us at all. I want an answer that's rounded to 3 places. So I use normal rounding rules. That 4 is not going to contribute. The 8's not going to contribute, but I have to be careful not to round this down to 515. I have to make it 5150. No decimal marking bar or anything on this measurement because I don't want to accidentally force extra significant digits. All right, then last one. We don't have to be as careful on the significant digits here just because the numbers are a little bit further away from each other. Our formula for friction, the force of friction is equal to the coefficient of friction, which is the Greek letter mu. It's kind of like a letter M. I didn't pick it. I don't know why it was the best choice. This is what we inherited from the past. But mu, that coefficient times normal force. If I'm looking for the coefficient, so it says here, determine the coefficient, then I can rearrange and solve this using algebra. That's going to tell me that mu, we're going to have to divide this thing around. So mu is going to be equal to the force of friction divided by normal force. Okay, well, what's the force of friction and what's normal force? So we need to figure that out. If it's going to take this much force to keep the object moving, then that means that must be our friction force. You got to push with that much, or otherwise friction is going to make things grind to a halt. So that's the first piece of information. Then the second piece is why we had to learn the previous question. So the normal force is going to end up coming from the total weight of the object, which normally we don't have. So we'll end up taking the total mass and multiplying by gravity to combine. Unfortunately, units here got cut off onto the next line, so I'm going to draw them back up here. And we want to work out basically what we did on the last one, and then throw it into this formula to finish up. So we've got 553, I'm going to leave some space, kilograms. Then that's going to be stacked on top of that pallet, which was 16.8 kilograms. We're going to add these together, which is 569.8 kilograms. Then rounding rules when we add. The placement of the last digit. This one's further left into the bigger numbers, so that's going to be our limit. We can't get an extra decimal place when we didn't know what this number was. So that's going to make this one turn into 570 because we're trying to round to the ones place, basically. Now, technically, to force that to be significant, we add a decimal at the end, and then that's going to be our total mass. Now I need this as a weight so that it can factor back into the rest of this. So stick this over 1, then on Earth 1 kilogram turns into 9.8 newtons because of gravity. That's going to give us 5586 newtons. Then to round, when we multiply it by number of significant digits, not decimal places. So this has 3 significant digits. So 1, 2, 3 places here. We look behind it in order to round. So that means that our properly rounded answer is 5590 newtons. No marking on the 0, no decimal, no bar. That's what we want because it has 1, 2, 3 significant digits. So that's the normal force. Then the friction force was in the question. We had to sort of interpret that information to get to it, but we do have it. Now we can plug this in and we can calculate mu. So force of friction, 3082 newtons divided by the normal force, which we had to work on, but we do have it now. Newtons and newtons will cancel, and that's intentional. So the coefficient here is just a number, typically a decimal number. From dividing these, 0.55134. So technically we're limited by the 1, 2, 3 significant digits in this one. The other one had 4, this one has 3, so that's our limit. Now, tiny difference in this and the answer key. These are written in Excel. Sometimes the answer choice is just rounded a tiny bit off. We get 0.551 compared to 0.552. Okay, and for this information, that's it.